Hello, welcome to Work Done, our last physics lesson together for a little while, so that's exciting stuff. We'll be going on to biology after this, looking at some stuff around diseases and spreading diseases, all of which is nice and relevant to our lives at the moment. So one lesson of physics to get through before we can move on to something a little easier going and a little bit less mathsy. And that last physics lesson is Work Done, so let's get on with it. These starter questions appear in your assessment for this, so it's worthwhile having that open or at least making notes of the answers as we go. Okay, so first question, which we should have done in the lesson, most recent lesson, is what is the equation for kinetic energy? 2, what is the gravitational field strength on Earth? So this is a number, nice easy number to remember. 3, state the equation that links mass, weight and that field strength. So this was the first lesson back after Easter. 4, what process would you use to remove a solid from a solution? So how would you go about taking something insoluble, something that can't be dissolved, out of a liquid? 5, what is the optimum temperature of the enzyme? Let's have a look at that graph there. See if you can find the optimum temperature. Remind yourself what optimum temperature means. And then finally, state the limiting factors of photosynthesis. So there are 3 of them. Good, so our answers. Kinetic energy is 1/2 times mass times speed squared. Gravitational field strength on Earth is 10 newtons per kilogram. Weight is equal to field strength times mass. That's our weight in newtons, the force we're exerting on the ground. You would filter a mixture to separate a solid and a liquid. 37 degrees was thereabouts the optimum temperature. That's normally a good guess because that's human body temperature. And then temperature, light intensity and carbon dioxide concentration are your 3 limiting factors for photosynthesis. Good. So work done then, our lesson to be getting through today. It is not too complicated at all, there's not too much to it. There is just a couple of equations to look at. So it's this equation for work done and this equation for power, and then being able to do these calculations. This whole unit of physics, it's just a lot of equations. It's about learning those equations and then being able to do them. Some of you that'll be a nightmare, some of you it will be ideal. The good news is either way, you've got plenty of time between now and your exam to revise these equations, to learn these equations, and generally how well students do in this physics exam is all about how familiar they are with these equations and how happy they are doing it. So it's nice and easy to revise for. Good. So previously we looked at gravitational potential energy and kinetic energy and how how objects can convert between them. So as their height increases, so does their gravitational potential energy. And then when they fall from that height, that potential energy gets converted into real energy, into kinetic energy as it moves. As its speed increases, that kinetic energy increases. Okay. But what we're looking at today is the idea that when you move things, when you increase an object's gravitational potential energy, it requires force to do that. It requires some effort on our parts. And this is what work done is. Okay. So moving an object requires a force, and the further you move that object, the more energy is required, the more work is done. So if you think of picking up a rucksack and moving it just across the room, that doesn't require too much energy. But if you carry that rucksack all day, you carry it on a long walk, it requires much more energy. It's much more hard work for you because you're carrying it further, and so it requires more force. Okay, So we have an equation for work done. It is this one here. It is equal to force times distance. So work done is measured in joules. It's just a form of energy. Force is in newtons, and distance is in meters. So you can have this triangle to relate those terms together if you like. So simply, work done is force times distance. This is one of the equations that you need to learn. You'll need it for your assessment, your assignment this week. So make sure you've got a note of it. Make sure you've got it next to you when you're doing those assignments. Okay, so we will have a practice of this this calculation, using this calculation. This question appears in your assignment. So make sure you follow me going through this because it will ensure you get a few marks. I will go over and do that on pen and paper now before magically reappearing on the presentation. Okay, so our first question here. A tyre is dragged 5 metres. It requires 340 newtons of force. How much work is done? So if we remember our equation, first mark will always be for writing down that equation. Work done equals force times distance. Good. My distance, work done, force. Tell the examiner that you know which each one of those are. So distance 5 meters, work done is what the question's asking me, and my force is 340. Good. Stick those into the equation. Work done is force times by distance, 340 times by 5. You might be able to do that in your head. No need to worry if you can't, you'll have your calculator with you. 340 times by 5, 1,700. And it's asking for work done, which is energy, so it's in joules. Make sure when you're answering these questions in your assignment that you're including units. Lots of you don't, and if you're finding it more difficult, make sure you include as much of your workings as possible. That's how you're going to get the marks in your actual exam. Good. Okay, perfect. Quickly now, this is a slightly more complex example. You don't need to worry so much about the numbers, but it just shows what this means in more of a real life scenario. So last year I ran the London Marathon. This is me in the middle of the London Marathon. There wasn't one this year, or it's been postponed, so I can still say that I've run the most recent London Marathon, which is nice. I'm sure I've never mentioned it before, so you'll all enjoy hearing about it. So during this marathon, I burnt 3,200 calories, which is a lot of calories. My watch reliably informed me of this. The recommended daily allowance for calories is 2,800. So by far the best thing about running a marathon is that you get to eat as much as you like afterwards, completely guilt-free. And this number of calories converts, if you go online, it will tell you that it's this amount of joules of energy, which is lots and lots of joules. It's what, just over 13 million joules of energy. You don't need to worry about that conversion. It's just out there online, should you ever be particularly interested. Calories in food is just a way of telling you how much food, how much energy is within that food. It's why Mars bars have got lots of calories, because they've got lots of sugar and lots of caramel, lots of other nice things, which means that there's lots of energy within it. Okay, so we can use this number along with the distance of a marathon to work out how much force was required to complete it. So a marathon is 26.2 miles. This is 42,195 meters, and I used this amount of energy to complete it. So we can calculate how much force is required just using that equation that we just looked at. So as ever, fill it out, answer it this way as I just went through on pen and paper. You can say your distance, your work done, and then finally we need to work out my force. So work done is equal to force times distance, and we can rearrange that to say force is equal to work done divided by distance. We divide both sides by distance to rearrange it. Okay, and then it's just a case of putting those numbers in. So my large amount of work done divided by my large distance to give me an answer of 317 newtons, which isn't actually that much in the grand scheme of things. It is just about possible for anyone to run a marathon, as I am very much a demonstration of. It is not as impressive as it sounds, but this amount of force does probably explain why I was very incapable of movement the next day. It's a bit more than I'm used to having to generate, and so I didn't feel that good. This, if we go back quickly, this picture here of me looking slightly surprised mid-marathon, this is because I asked my girlfriend to take some pictures during the marathon, because they charge you an awful lot of money to have official pictures taken. So I thought, nice easy way of saving money, just get Ellie to take a picture. This is one picture that I got from the day. The other picture that I got from the day to commemorate my completing of the London Marathon is here. That's me. Great. Cool. So, other equation we need to look at is power. And this is nice and simply a measure of how quickly work is done. So again, an equation for this. Power is equal to work done divided by time. Work done still as energy, still measured in joules. Whenever we look at time in physics, we should be thinking of seconds. And then the unit for power is watts. It's the oldest physics joke, oldest science joke. Watt is the unit of power. Yeah, easy way to remember it. Make sure you do. Again, just an equation that you need to remember and be happy using. You should be familiar with power anyway, because it is on the back of every microwave meal. Your microwave is able to supply a certain amount of power. The more powerful your microwave, the less time it will take to cook your meal. It will be able to transfer more energy quicker if it's a higher wattage microwave, and so you need to put it in for less time. In the same way, people that completed the marathon much quicker than me, they did that because they were, or their muscles are more powerful. They're able to do that same amount of force. They're able to transfer that same amount of energy. They just do it much quicker. Okay, good. So we'll look at a couple of examples, starting with this one here, and then an exam question. Again, I'll head over and do that on pen and paper. So thank you very much for watching this bit. Make sure you complete the assessment afterwards and use these examples to help you through. Good, bye-bye. Okay, so this is now looking at power. So it says it requires 1700 joules of energy to drag the tyre 5 meters. This takes 20 seconds. How much power is required? That should be a 5 there anyway, if my handwriting's terrible. Power equals work done over time. Sorry, I'm back to handwriting these. I know we had nice printed copies last lesson, but my printer's run out of ink, and everyone's sold out of ink, unsurprisingly, because everyone's working from home. Okay, so this question, power, work done, time. So power is what the question is asking you. Units are what? Work done is your energy, 1700, and the time is 20 seconds. Okay. So in these questions, to make them a little more tricky, they will often put the time in minutes. We'll have a look at one of those in a second, and they'll often include things like a distance in there to try and trip you up, try and make you think which equation you need to use. As it is, this one's nice and simple, exactly as it appears. You do your work done divided by your time to get your answer. Which is 85, and your units are watts. Okay. Make sure you're including your units. Make sure you're using more workings if you need them. In terms of rearranging this equation, if you need to, it is just power times time equals work done. Time is therefore equal to work done divided by power. Make sure you're happy using your triangle, happy rearranging these questions. The assignment, your questions will ask you to do lots of those. There you go, I've just shown you how to do them all. So, second example. An 850 watt microwave is used to heat a meal for 3 minutes. How much energy is transferred? So it's the same equation as before. It's still using power equals work done divided by time. So the only difference here is that they say energy is transferred. That is my work done. Okay, because work done is measured in joules, you're expected to know that it's energy, and you're expected to know that those two things are interchangeable. So you can do just as we did before. And go through your different terms. So power is 850 watts. Your work done is what I'm trying to calculate. And my time, it says 3 minutes. 3 minutes. Okay. We need this to be in seconds. So our first job is going to be to do 3 times by 60 to get it into seconds. If you didn't do that in your question, you would drop a mark. But we're going to make sure we do it. So now it's a case of putting this into my equation. So you can say 850 is equal to my work done, which I don't know, divided by my time, which is 180. Okay. So to find out this here, I need to do 850 times by 180 to find my answer. Which comes out at 153,000 joules. Okay, so 153,000 joules of energy, which is a reasonable amount of energy, but it takes a reasonable amount of energy to heat food, to heat water. You might get asked to give this in kilojoules, which means dividing by 1,000, which is 153 kilojoules. Questions like this, when you're expected to rearrange the equation, it's always worth an extra mark. If you're expected to convert time, it's always worth an extra mark. So these might be a bit more complicated, but you get more marks for your money. And then finally, our exam question, which is tricky. Particularly tricky as I had to try and draw my stairs, which is remarkably difficult, but those are meant to be my stairs. So it says Jana walks upstairs, and it shows you some stairs in case you're unfamiliar with them. We should all be nice and familiar with stairs at this point in our lives. So height of one stair is 0.15 meters. Jana walks 4 stairs. It tells you the gravitational field strength and it asks you how much work is done. So if this is back to asking about work, there is no time in here, so it can't be my power calculation, but I do have a distance, so it's going to be work done equals force times distance. If nothing else, you can write that down to get yourself a mark. And your distance, well, it's 4 stairs, so 0.15 times by 4 to find out your distance, which comes to 0.6 meters. Your work, we don't know, so we can leave it as a question mark. And our force, if we think about this and think back to our previous lessons, we can work this out. Force is equal to mass times by gravity, and it gives me a mass in my actual question. I've forgotten to write it down here, but it does give you a mass. It says that she weighs 50 kilograms, and it gives you gravity, which is 10. So you can work out her force, the force she's capable of creating, by doing 50 times by 10, which equals 500. And it's force, so it's newtons. And then you can put this into your equation. Work done is force, 500, times by distance, 0.6. Because she's having to take that force up some stairs. How much energy does that take? 300. It's work done, it's energy, so it's in joules. So that should be your final answer. Okay, so this is expecting you to bring together a couple of different equations, and so it would be worth more marks. It's just a case of making sure you read your question properly. Okay, good. That's it. That's done with physics. Have a go at the assessment. Look forward to biology. Keep safe. Bye-bye.